Hello there, Mr. Sutton here, bringing you the BC Calculus 7-9 Extra Practice Number 1 solutions on integral and P-series tests. For this problem, I want to determine whether this series converges. So on this one, there isn't a whole lot else that's going to work. I mean, if you try nth term test, this goes to 0. Ratio test doesn't work out so well. It's not a P-series. So at this point, we try the integral test. So this is a function that is continuous, positive, and decreasing, at least for all n values of 3 or greater. Anything less than that, all bets are off. So we write that out. This allows us to actually use the integral test. So we're now going to take the integral of 18 over n ln of n from 3 to infinity. Now this is an improper integral, so to do this, I need to set up a limit as b approaches infinity from 3 to b of all this stuff. And in order to actually integrate this, you're going to end up needing substitution. So let's let u equal ln of n, and then du is going to be dn over n. But we need to swap back in for the dn, so let's multiply both sides by n to get dn by itself. Now can we exchange that for n du? We also need to change out these limits of integration for u values, because these are n values right now. So if n is 3, then u is going to be ln of 3. If n is this b value, well, we have to change that to ln of b. Plugging it all back in, we have b approaching infinity, integral from ln of 3 to ln of b, 18 over n times u, and then dn is replaced with n du. So all those changes. Now these n's conveniently cancel. And we're now free to just take the antiderivative of 18 over u, which is 18 ln absolute value of u, from ln of 3 to ln of b, still approaching infinity with our b value. Plugging all that in, we've got 18 ln of b, and I'll actually pull the 18 outside my evaluation box here. So we've got 18 times, and now inside we have ln of b minus ln of 3. As b approaches infinity, this first term is going to go to infinity, so that actually is going to diverge our whole integral. Since this integral diverges, and we've shown that we have these conditions up here, continuous, positive, decreasing, we've shown that this original series also diverges by the integral test. For this one, trying to find the convergence or divergence, this series is a p-series with a p-value of 1/2. This is really n to the 1/2 down here. Since that is less than or equal to 1, that means this is going to diverge by the p-series test. For this one, we have a p-series with a p-value of 3. Since that is greater than 1, that means this series converges by the p-series test. On this problem, we have a p-series of p-value of 2. Since that's greater than 1, this is going to converge by the p-series test. For this problem, we notice that we have a p-series. This is really n to the 1/3, so we have a p-value of 1/3. Since that is less than or equal to 1, that means this is going to diverge by the p-series test. To make this one a little bit easier to do, I'm going to rewrite this as 1 over n to the 3/2. And here we see that we actually have a p-series with a p-value of 3/2. Since that's greater than 1, that means this one's going to converge by the p-series test. For this problem, we have this table showing Riemann-sum approximations to integral from 0 to 1 of 1 over x dx with right-hand endpoints, so basically RRAM. And we want to find which statement describes the limit of the Riemann sums as n approaches infinity. So here we had some limited n values, but what if n approaches infinity? Okay, so to do this, first off, if you're basically looking at this thing as n approaches infinity, you're asking about the integral from 0 to 1 of 1 over x dx. These two things are the same thing. This is just the Riemann sum version of this integral. So really, they're just asking about, what does this integral evaluate to? This is actually an improper integral since we have a discontinuity at the endpoint 0. 1 over 0 is undefined. So we need to rewrite this with a limit. I'm going to write this as limit as a approaches 0 from the right of a to 1, 1 over x dx. And now let me take my antiderivative. That's going to be ln of absolute value of x, evaluated from a to 1. So this is just going to be ln of a minus ln of 1. And we can take off the absolute value because I'm plugging in positive numbers if I'm plugging in everything greater than 0 and less than 1. So now ln of 1, that's just 0. That's not an issue. But ln of a as a approaches 0 from the right. So the ln function does one of these kind of deals, kind of looks like an R. As you approach 0 from the right, you're heading down an asymptote at 0, and you're going to negative infinity, which makes this whole thing negative infinity. So this actually does not exist. And we have an answer choice for that. The limit of the Riemann sums does not exist because this integral does not exist. So that would be the best answer for this one. The other answers, they have the limit of the Riemann sums being finite numbers, which is clearly false if we're going to negative infinity. Limit of the Riemann sums doesn't exist because this term does not approach 0. Well, as n approaches infinity, this is definitely going to 0. Limit of Riemann sums does not exist because it is a sum of infinitely many positive numbers. Well, we've seen all sorts of infinite sums that do converge. Infinite geometric series, for example, with r values of less than 1. So E is the best answer out of all these. For number 6, they want to know for what values of x does this series converge. Now this is kind of a tricky sort of question. It sounds like they're asking for an interval of convergence, and we're used to using the ratio test and all that kind of stuff to figure this out. But this one can actually be tackled with the p-series test. So let's say that we have an interval, we have a summation rather of n to the x. That's our nth term. We'll put that inside our sigma from 1 to infinity. Well, we can actually rewrite this as 1 over n to the negative x. Writing it in this way is completely legal, and it also allows us to express it as a p-series with a p-value of negative x. In general, we know that a p-series will converge, and that's what we're interested in, if the p-value is greater than 1. That means that our p-value, which is negative x in this case, must be greater than 1. Well, if negative x is greater than 1, that means that x has to be less than negative 1 if we divide both sides by the negative. Just be careful to reverse that inequality, right? Basic algebraic stuff for inequalities. So that's going to give us answer choice B. For number 5, they're saying f is a positive continuous decreasing function that's the nth term of some converging series. This series converges to k specifically, so we want to know which of the following is true. Now, the language of this question, positive continuous decreasing function, this is the language of the integral test, which says that if the integral of such a function converges, then the series involving this function as the nth term is going to converge. Here they're telling us the series does converge, so that means that the integral that's based off of this also has to converge. That would be the integral from 1 to infinity of f of n, which is basically what choice D is saying, that that integral converges. But let's go through all the answer choices, and we'll just see why choice D is the only one that's actually true. So choice A, they're saying the limit of the nth term is k. This would be true if our series converged to 0. For a series to converge, the limit of the nth term has to be 0. But if k is some number bigger than 0, then this series would actually diverge by the nth term test for this to be true. So that can't be true for all k values and still have this series converge. Next one, they're saying integral from 1 to n of the function is k. Well, this is really out in left field. Whatever happens with an infinite series doesn't really tell us a whole lot about finite integrals. It tells us about infinite integrals, but not finite ones, and n is a finite number the way this is written here. Okay, so this next one, choice C, this is saying pretty much the opposite of what the integral test says. If the series converges, the integral has to converge, not diverge. So C is the opposite of what we want. Choice D is exactly what we want. If the sum converges, the integral converges. And choice E, this one's a little trickier. They're saying the integral converges to k itself, but this doesn't necessarily have to be true. For the series to converge to k, the series is basically a Riemann sum approximation of the integral. That means it's not going to give you the exact value of the integral. So all of these reasons, choice D is the only one that makes sense. On this problem, they want the interval of convergence for this series. Now, since this is not a geometric series, we instead need to use the ratio test to start this. So let me take the n plus 1th term. That's going to be, so we're going to have the limit as n approaches infinity, absolute value of, and now n plus 1th term, which is this craziness right here. It's all of this stuff, and we have 2 times n plus 1. And then we're going to have n plus 1 to the 3 halves instead of just n. And we're going to divide this by the nth term, which is just what you see here in the sum and. Let's same change flip this stuff. In my numerator, I've got 4x minus 5 to the 2, n plus 2. Oh, and we'll also have an n to the 3 halves up there. Denominator, I've got n plus 1 to the 3 halves and 4x minus 5 quantity to the 2n. Let's simplify these a little bit. Can't do anything with these n expressions because we have n versus n plus 1, but this infinite limit will take care of that down the road. For now, though, we can simplify these 4x minus 5s. Subtracting the exponents, I really just have 4x minus 5 squared up top. And now we also have a n to the 3 halves, and we have this n plus 1 to the 3 halves is the only thing left downstairs. As n approaches infinity, we can forget about this little plus 1 in here. So it's really just n to the 3 halves over another n to the 3 halves, which is going to cancel, leaving us with just 4x minus 5 squared. So we'll set this less than 1 as part of our ratio test. And if we solve this, we'll find at least an initial interval of convergence. So we can square root both sides. And I'm also going to make this -1 less than the stuff inside less than 1 to get rid of that absolute value. Add 5 to both sides. We've got 4, 4x, and 6. And then dividing everything by 4, this is going to be 1 less than x less than 3 halves. Or is it? We have to test the endpoints now. So if we have an x value of 1/2, let's see what that does to our series. That's going to give us, let's see, this is 4 minus 5 is really -1, but we're raising it to an even power. So this is really just 1 over n to the 3 halves when all is said and done. And this is going to be a p-series with p greater than 1, so that's going to converge. But let's quickly look at my other endpoint, 3 halves. So 4 times that would give me, let's see, 6 minus 5, which is also 1 over n to the 3 halves. So these are exactly the same series, it turns out, because of this even exponent. These are both p-series, both p 3 halves. So since that's greater than 1, these are both going to converge. And we're going to write this as 1 less than or equal to x less than or equal to 3 halves.